The effect of the air is usually neglected in discussions of amusement park physics, but interaction with the air is at the heart of exciting ride experiences in the new Sky Roller ride. It may seem like a quiet circular motion around the tower, with a panoramic view of the surroundings. However, by tilting the wings to catch the oncoming air, the planes can be made to roll higher and higher, and ultimately to make a series of full turns. The forces in this ride are sufficiently small that they may be measured using the built-in sensors in a phone. The phone can also measure rotations around the 3 axes, as well as air pressure. Here are the data from the start of a very quiet ride. As the plane moves up, the air pressure drops, and while moving around the tower, the plane also rotates around a vertical axis. This rotation is known as yaw, and the clockwise motion corresponds to a negative sign. After a while, the plane tilts, and the rotation vector gets a component along the negative y-axis in the system of the rider. This is referred to as a pitch. But let us first consider the forces on the rider. In the beginning we experience 1g. It is the force from the plane compensating the force of gravity, which always acts. During the circular motion around the tower, plane and rider are accelerating towards the center of the circle. This acceleration is purely horizontal. The force from the plane needs to provide the force required for the acceleration, while also compensating for gravity. The yellow vector shows the force from the plane divided by the mass of the rider. This vector defines the direction which is experienced as up during the ride. If you don't tilt the wings, your z-axis will point in that direction. What you experience is also what the accelerometer sensors measure. As the plane rotates around the direction of motion together with the rider, the force from the plane varies between the y and z coordinates of the rider. When you rotate, also the sensor coordinate axes rotate together with you. This graph shows the forces during the start of a ride. The lateral forces are most sensitive to the small changes in angle. And this diagram shows the relation between lateral forces and the orientation of the rider. During our first rides in the Sky Roller Aerospin at Liseberg, we collected these data. First we show only the lateral component. I collected data with a wireless dynamic sensor system from Vernier, carried in a data vest.
And this is my sensor. It's designed around the 6DoF sensor MPU 6050 and to be as small as possible to be able to mount on the heartline on the rider's body. It's battery powered and saves the data on an SD card.
Marcus, who had practiced before on the first Sky Roller Götteflug at Belantis, managed more than 40 spins, whereas I didn't quite make it all the way around. How does the fast spinning affect the body? The data show only small effects on the total force due to the rotation. Still, some riders complain about a light headache after an intensive spinning ride. Intuitively, we would expect to see an effect of the rotation in the accelerometer data. There is in fact a small difference between the lateral and vertical forces. However, the sensor is placed close to the axis of rotation, so the centripetal acceleration is small. The head is further away from the axis, and we can estimate the acceleration of the head using the expression r omega squared, which may reach 2 or 3 g's. But riders who feel uneasy can of course in principle slow the rotation by changing the orientation of the wings. And in any case, the ride soon comes to an end. You can check the scoreboard for the number of spins of each plane. For most planes it's likely to be 0. Getting the planes to make full turns is not that easy. And there is no way your plane will spin if you don't want it to. It is perfectly okay just to enjoy the views from the top.